In today's class, we will go through electrophilic substitution reactions in aromatic ethers. Right? We have done similar type of reactions in phenols while doing phenols. When we did electrophilic substitution reactions in phenols, nitration, sulfonation, Friedal reactions. So similar thing we would be doing here, right? And this is your aromatic ether. I've drawn the benzene ring. It's same as this, or R, any R, you can write it as R. Right? Now we know that oxygen has two lone pair of electrons, same are shown here. Now electrophilic substitution reactions. When we say electrophilic substitution reactions, that means electrophiles which are positive reagents, right? For example, your NO2 plus, your bromonium, your SO3H, or the others are CH3 plus. All these are electrophiles, right? Now these are positive reagents, so they will attack at sites of high electron density, right? Now in the benzene nucleus, these will attack at sites of high electron density. Now we need to see where we have sites of high electron density and how these high electron density sites are created, right, in aromatic ethers. If you look at this, you have this OR, right? This is your benzene nucleus, right? You have two lone pair of electrons. Now what happens is this lone pair of electron will enter into the benzene nucleus, right? And it will enter into conjugation with the benzene nucleus, right? It will start moving inside the benzene nucleus, right? And will create sites of high electron density, because this is a lone pair of electrons, so it can create sites of high electron density, right? You can see it is moving. First it came here, so now this is your negative site, right? Then it went here, this is your negative side, and it went here, this is your negative side. And if we know from the study of benzene that these three sites are ortho sites and parasites, right? These are your ortho and parasites. So electrophiles will attack at ortho and parasites in aromatic ethers, because ortho and parasites contain regions of high electron density because of plus R effect, right, of alkoxy group, right? This is an alkoxy group, right? And it shows your plus R effect. Plus R means resonance effect, where your lone pair of electron is in resonance with the benzene nucleus or in conjugation with the benzene nucleus, right? Thereby creating sites of high electron density, right? Now, since I said in the beginning that we have done this in case of phenols also, but similar thing is done by phenols also. Phenol will also create sites of high electron density, but what happens in case of phenol is the ring would get activated to a higher extent, right? The OH group, right? This OH group will also create sites of high electron density. When we say it's creating sites of high electron density, we say that the ring is getting activated, right? So the ring is activated, right, by this electron push inside the nucleus. This plus R effect is more in phenols, right, compared to in aromatic ethers, right? That means this OH group will activate this benzene nucleus to a higher extent compared to phenols, right? Compared to this alkoxy group in aromatic ethers, right? So since phenol will activate benzene nucleus to a higher extent compared to alkoxy group in aromatic ethers, so your electrophilic substitution reactions in aromatic ethers would be less, right? The extent of electrophilic substitution is less in aromatic ethers compared to phenols, right? Because of less activation of benzene nucleus in your aromatic ethers, right? So just remember this. Electrophilic substitution reactions, right? So aromatic ethers, these are less reactive, basically. Due to less activation, they are less reactive. Aromatic ethers are less reactive compared to phenols for electrophilic substitution, right? Now coming on to reactions, let's look at halogenation. Right, let's look at halogenation. It will react with bromine in presence of halogen carrier. If you remember, iron fillings, right? So it will form ferric bromide, and in case of the work of halogen carrier, if you remember, we have done this in the previous lectures, is that it will introduce this halogen, right? It will form this bromonium. It will break this and will form this electrophile bromonium. Right now, this bromonium will enter into the benzene, will attach to the benzene nucleus, right? Will react with the benzene nucleus. So halogen carrier will carry this bromine atom to the benzene nucleus, right? So what will form is Br, 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 right? The name of this product is 2,4,6 tribromo, right? 2,4,6 tribromo 1 anisole, right? Or I'm sorry, 1 methoxyphenol, sorry, 1 methoxybenzene. I'm sorry. This is your 2,4,6 tribromo, right? 1 methoxy, right? If this is your CH3, right? Let's take this as CH3, methoxybenzene, or 2,4,6 tribromo anisole, right? This is your anisole. If you remember, this compound is anisole. So this is your 2,4,6 tribromo anisole, right? Now there are two types of reactions here. If you do the same reaction in carbon disulfide, right? If you do the same reaction with bromine in carbon disulfide, it will form ortho and para product. It will form ortho, right? And para product. These, right? Similarly, if you look at nitration, if we do nitration of anisole, right, with nitric acid and concentrated sulfuric acid, right, it will form ortho and para product, like this. It will form ortho. Ortho would be this. Since we are doing nitration, so your electrophile would be nitro, right? The other would be your para product, like this, right? So ortho, nitro. The name of the product is, it's ortho bromo. This one is ortho bromo anisole, para bromo anisole, and in case of nitration, it's ortho nitro anisole, and para-nitroanisole, right? Or you can write it as 2-nitro in IUPAC system, 2-nitro 1-methoxy-benzene, right? And in this case, it is the para product is named as, this is at position 4, so this is 4-nitro 1-methoxy-benzene, right? Just know how to name these. Now let's look at sulfonation, right, where a sulfonic group would be introduced. Right? Sulfonation would be done in presence of concentrated sulfuric acid. Right? When treated with concentrated sulfuric acid, right, with concentrated sulfuric acid, it will form ortho and para sulfonate. This is ortho sulfonic, right? This ortho, the sulfonic group is at ortho position, right? So the name of the compound would be your orthoanisole sulfonic acid, right? Ortho, this is your anisole, this is orthoanisole sulfonic acid, and this is your para-anisole sulfonic acid, right? And since sulfonic is at 2 position, so this is 2-sulfonic, right, 1-methoxy-benzene. This is 4-sulfonic 1-methoxy-benzene, right? And we have famous Friedal reaction also, right? Let's look into Friedal reaction, where your anisole will react with methyl chloride, right? It will react with methyl chloride and anhydrous aluminium chloride to form orthomethyl anisole and paramethyl anisole, right? It's OCH3 plus methyl chloride in presence of aluminium chloride. This is your famous Friedal reaction that we have been doing quite a long time now. Right, what it will, the methyl group will enter here at ortho and para positions. Right, here in this case here. So this is your orthomethyl anisole, this is your orthomethyl anisole and paramethyl anisole. And if you want to name it in IUPAC naming convention, the name of the compound is, this is your 2-methyl 1-methoxy-benzene, right? Now we have other type of Friedal reaction also where you take acetyl chloride in place of methyl chloride. If I take in place of this, if I take CH3COCl, then this acetyl group, right? This acetyl group will introduce at ortho and para positions, right? So as we know that Friedal reaction is a way to introduce methyl group or this acyl group into the benzene nucleus. This acetyl group into the benzene nucleus. This is your acetyl group and this is your methyl group, right? So we are introducing acetyl or methyl group in benzene nucleus through Friedal reaction, right? This is what we basically do using Friedal reaction, introduction of methyl or acetyl group at ortho and para positions in benzene nucleus mainly, right? I hope all this is clear. Thanks.